What's the
chair now?
Well, yeah.
What's the chair now?
I don't know. This is sort of one of the things.
You say so, yes, they're great. They said they're all falls in quality things. Okay, welcome back to the final session of the day. So before we go into Nicole's talk, I just want to remind you that this morning Ursula made a very enthusiastic plea for young people to get more involved in the questions and giving comments, whatever. I am not as eloquent as Ursula, so I'm going to resort to bribery. So in this session, the best question, the best comment, the best joke, the best dance by a young person.
How young?
By my criteria, right? So I decide who's young. Will we? Delicious. Canarian honey rum. Okay? So come on.
Discrimination.
So no bias because I'm both. Let's start with Nicole.
Okay, so thank you for having me here. I'm Nicole Reindl, group leader and permanent staff member at Heidelberg Observatory, and I present you the first detached double eclipsing, double lined and double degenerate system inside a planetary nebula. This work was done in collaboration with Dave Jones, Todd Hilbeck, Matti Dorsch, Nick Chorney and Max Ritzbolay. So why are double degenerates interesting? Well, some of them, if close and massive enough, can be gravitational wave sources. They are also important to test the physics of common envelope evolution. They may be progenitors of type 1a supernovae, or if they merge and not produce a supernova, they may also become exotic stars like highly magnetic stars or stars that show various exotic surface compositions. Why is it now cool to have a double lined and double eclipsing system? This is because we can derive the inclination angles and the radial velocity amplitudes of both stars, and this in turn gives us, at least in theory, high precision measurements of the masses and the radii of both stars, which are, and that's important now, independent of evolutionary calculations, so we can use them to actually test stellar evolutionary calculations. So far, I list here the number of double lined and double eclipsing systems, double degenerate systems that are known. So amongst white dwarfs, we have 13 of these systems. Amongst the hot subdwarfs, so naked pre-white dwarfs that do not have a planetary nebula, there's only one system known. And amongst central stars, we now already have 2 systems. I put here in blue now the numbers. The first number tells us how many white dwarf candidates do we know in our galaxy, thanks to Gaia, and also for the hot subdwarfs and for the central stars. And the second number that I list are now the percentages of how many of them are really double lined and double eclipsing. So you can see that for the central stars, we already detect 20 times more compared to the white dwarfs and the hot subdwarfs, which is nice, but we should keep in mind that our stars are bigger than white dwarfs, so of course the chance to detect an eclipsing system is larger. The previously known system was HEN 2/28, and this is an overcontact system, as you can see in this nice video made by David Jones. And if I find the mouse, then you can see it looks a bit like a peanut. So when we see both hemispheres of both stars, we have the maximum flux. And then the light, this is not playing here. Okay, so it looks like a peanut and the light curve looks different than the one I'm going to show you now. This is now the one from PA13, which the talk is about. And I'm stuck here with the slides. Why the slides are not moving anymore? This is the video? No.
Don't blame the video.
You have a window up there that you're supposed to respond to, it looks like.
Okay. Audio settings. Excuse me. Oh, yeah. Oh, okay. Now, so the talk is about PA13, and that's a detached system, which becomes obvious when we look at the light curves. So these are light curves from CTF in the green and the red band. And we can see here two eclipses. It's double eclipsing, with one eclipse being a bit deeper than the other. And we actually discovered that already a few years ago now, but it's also now independently been published, at least the light curves, with both authors mentioning that it's a double degenerate and double eclipsing system. However, what we did not publish it yet, but what we did was that we fitted the light curves. So Dave and Todd fitted the light curves, and what that already told us that both stars must have similar luminosities. If they have similar luminosities, chances are that we might also see the lines of both stars. So what we did next was to obtain spectra with the GTC OSIRIS and the LBT MODS, taken at the phase where we would expect a maximum RV separation, and looking then at helium-4 686, we indeed found it's double lined. So in the OSIRIS spectra, you can see here the weak line star is red shifted, and here it is blue shifted. So what we did next was to obtain, because it's a very observer-friendly system, you can observe it on both hemispheres. So we also applied for time with VLT X-Shooter, which has a resolution of about 10,000. And we got phase-resolved spectra. In 2002, due to bad weather, we only got 8 spectra with not so great signal to noise, but we got again time and in 23 and took 15 additional spectra. Also, we obtained more photometry. How did we analyze the data? First of all, we measured the system velocity using a narrow oxygen nebula line. And then in an iterate approach, we fitted the light curves and then carried out the spectral analysis based on the what we knew from the light curves. So we had some star parameters for the temperatures and radii. And so we fixed the light curve ratio, the surface ratio in the spectral fit, because the spectral fit is not very sensitive to the light curve ratio, and then obtained the radial velocities, temperatures, the surface gravities, and the helium abundances of both stars. And then we used Philby to do the light curve fitting again, to again iterate with the surface ratio, get the inclination angle, the masses, and the radii of the systems. Here you can see now parts of the X-Shooter spectra taking at 2 different phases. Here, for example, we see H beta. And here, this light gray region we excluded from the fit, so we still see a narrow nebula line. And what also becomes obvious, the line of the hotter star is much weaker than the line of the other star. So we obtained now the following parameters. So the first star, which is the bigger one, is cooler. It has a temperature around 50,000 Kelvin, while the other star, there we can derive the temperature not very accurately, is a factor of 1.5 hotter. It's also slightly more compact, and both stars have similar helium abundances around the solar value. Okay, these are now the fits to the light curves. So here we have the larger, cooler star in front, and here it's the other way around. That's the CTF light curve. The dark green is additional photometry that we obtained. Here CTF R-band, and here some I-band photometry. And at the bottom you can see now the radial velocity curves that we obtained for the two stars. And you can already see they are pretty similar, which tells us already that the masses must be similar. Now, so here the period, that's the binary mass function. So from the light curve fits, we get the period and the inclination angle. And then what we need next are these radial velocity amplitudes, which we get from the RV curve fitting. And then we can calculate the masses of the two stars. Now here come the masses. So from the dynamical masses, from the RV fitting and light curve fitting, we obtain for the larger and cooler star a mass of 0.5. You can see the arrows are pretty large. And for the weaker line star, which is hotter and more compact, we obtain a mass around 0.45. In this diagram, I'm sure is now the Kiel diagram, where we have the temperature and the surface gravity here. So parameters we can measure from spectroscopy with the large arrow bars for the hotter star. And here's the cooler star. The black lines are the post-HEP evolutionary tracks from Marcello, and the dashed lines are post-RGB evolutionary tracks and labeled with the masses. And if we now say, okay, for this star, we can derive the parameter pretty accurately and we trust that, then it actually would be a helium core white dwarf, pre-white dwarf. And if we combine this information that the blue star needs to be less massive, then it actually should sit somewhere around here and also have a lower mass. Here, the open circle indicates what the light curve fits actually tell us. However, the spectroscopy prefers a higher surface gravity. But as I said, the lines are weak, so the parameters cannot be determined very accurately. Next thing that we did was to calculate space velocity. So U points into the direction of the galactic center, V into the galactic rotation, and W perpendicular to the galactic plane. And why do we do that? And how do we do that? First, you need the distance, proper motions, and the system velocity that we measure from the nebula line. And what you can then do, you can put it in this Tomre diagram and compare it with the velocity distributions of main sequence stars, where you can measure metallicities. And based on these metallicities, they have different velocity distributions. So halo stars, which are shown in blue, have this velocity distribution, thick disk stars, this velocity distribution, this one, thin disk stars. So that tells us our star is actually a halo star. Halo is pretty old, and if you compare the age of the halo with main sequence lifetimes of low metallicity stars, then that tells us actually that the star that initiated the final common envelope evolution must have had a mass around not much more than 0.8, 0.9 solar masses. So how could this system have formed? Well, that's actually a question to you, and maybe the question is good enough to get the string from Dave. But so from what I understood is that the first mass transfer episode in pre-helium core white dwarf binaries is quite uncertain how it works. But they should have two mass transfer episodes, with the second one then, of course, being a common envelope evolution. Requires also low mass progenitors, which makes sense when we have a halo star. Alternative scenario could be a double core evolution, where you need a mass ratio close to 1. And within that scenario, the primary fills its frost slope at the time when the companion has evolved off the main sequence. And then the envelopes of both stars are ejected simultaneously. However, with this scenario, the question is then, why do we have stars with such different parameters? Why is the one so much hotter and compact compared to the other one, which is cooler and larger? Okay. Then what could be a possible outcome of this system? Here we have now the period on this axis, logarithmic, and here the total mass of the system. And the black data points are all known double degenerate double white dwarf systems. And this one is the HEN 2428, so this peanut shaped central star. And this is now the location of PA13. The dashed line indicates the Chandrasekhar mass, and the teal dashed dotted line indicates which systems will merge within a Hubble time. So you can see it's close to will merge, but the parameter, the masses might also be too less. But within the error limits, it could still be everything. So we hope we can constrain it in future better. And have then better constraints on what could it be. Conclusions is that our system is now the already second double-lined and double-degenerate eclipsing binary nucleus inside a planetary nebula, and it's the first system that is detached. And currently the analysis is complicated because one star has a weaker line than the other. And our preliminary results suggest that both stars are likely helium core pre-white dwarfs that may merge or may not merge in future. Thank you.
Questions with alcohol on the mind? No questions?
Bit beside the point perhaps, but you calibrated the velocity from the 4363 line, your 3 line.
At the system velocity.
Yes, I was surprised that line is so strong in your nebula. It's not normally in a very strong line, so is that
no?
unusual
I choose a narrow line because like H alpha is very broad, and with narrow lines you can measure more accurately. And also I wanted a line that is inside the blue channel of X shooter, where we also measured for the velocities of the stellar lines. And like for example with the H beta line, I also tried H beta. But there you actually, to measure it accurately, you need simultaneously also fit the lines of the both stars, because when you have line blends, it's not so easy to measure the velocities.
Okay, well I would recommend that you also look at your nebula lines. See that they are the usual line ratios, because 4363 is normally very faint.
Yes, but it was sufficient to measure within a few tenths of within 4 kilometers per second.
Hi, nice talk. I was wondering, I might have missed it, but when you're fitting the light ratio over 2 stars, are you assuming that it is constant in wavelength, or do you predict the wavelength dependency of the light ratio based on the difference in effective temperature?
The light curve, from the light curve we get the volumetric ratio, but both stars have similar temperatures, so or at least very hot temperatures.
Right, thank you.
When was the nebula created? Do you have?
I calculated it. What was it? Let's say 20,000 years kinematical age, if I assume 20 kilometers per second expansion velocity.
And does that work with your HR diagram?
post RGB evolutionary timescales are longer by a factor of 4 or so. But on the other hand, when they come fresh out of the common envelope, I don't know if you can really trust this evolutionary timescales. They might be out of equilibrium or something. So, yeah.
It's likely created when the last white dwarf became a white dwarf.
You missed yesterday. You missed yesterday, but yesterday we already said that we don't trust any of the start times for evolutionary times. Okay, so I think we have time for one more. Lawrence was. No, are we finished? Well, one more one next.
Yeah, I wanted to know what information is about the nebula? Citation, morphology,
Yeah,
light ratios.
this I actually wanted to say, that's the best picture or only picture I could find. So I'm looking at you. I think it's a system that would be worth to get more information on the nebula.
Nebular spectroscopy, there is no nebular spectroscopy.
No, well, for us, the nebula is annoying if you want to analyze it. So we just try to get rid of it.
Well, I think there is room for improvement.
Yeah.
Okay, let's thank Nicole again. Well, next we have Bruce Rubner, who's going to continue the debate on how protoplanetaries are not the same as all of our binary planetaries.
Next.
Okay, well, thank you. It's a pleasure to be here, talking about testing the binary hypothesis for the shaping of proto or pre-planetary nebulae. Work done in conjunction with Heinz von Winkel and Wen-Shen Liu. I just want to say a bit about, maybe start by defining protoplanetary nebulae, or what I have in mind when we talk about that. These are objects in transition from the AGB to the PN evolutionary phase. We started detecting them after the IRAS satellite. So I'm going to bring a little historical perspective to this talk. Looking for objects that had cool dust shells around them, but not so cool as to be planetary nebulae. So we find the central stars are G to K, GK to B, supergiant spectra with appropriate temperatures and luminosities. Once we got imaging, we could see that there were small nebulae, few arc seconds around them in visible light, expanding gas, cool dust, and work done then following up these objects to look at detailed abundances, showed carbon and S process enhancements in many of these, and Hans von Winkel is involved in that, oxygen or carbon-rich dust. And I make the note that not all post-AGB stars are going to be progenitors for planetary nebulae. Some will evolve too slowly, the nebula can be gone, or they don't have much of a nebula around them, not much mass ejected. Okay, so initial program, this is a while ago. Once these objects were first identified, I asked the question, do they vary? What might that look like? So I took the opportunity of a sabbatical at the Dominion Astrophysical Observatory to start a program looking at velocities, what's happening with these newly identified stars, and found that all of them varied. I had data over a 5-year period, found periods that ranged from about 35 to 135 days, but follow-up light curves in conjunction with this showed that this was due to pulsation in the stars and not ascribed to binarity. So no evidence from this early sample of binarity with periods at least less than a few years. Now, now I'm up here talking about the search for binaries and protoplanetary nebulae. I mean, why is that interesting? Of course, we know binary companions can affect the composition, evolution of a star, so it's interesting in general. But during these 2000 or late 90s, early 2000s, we started getting HST observations of these, and we saw that many of them had bipolar or elliptical or multipolar images and morphologies. And there were debates at these early conferences. Is it due strictly to binaries? Is it due to magnetic fields? And there's a lot of inference then that arose that if they're bipolar, that a binary must be involved. And Ursula championed that at some of these meetings. So specifically, the binary can affect the shaping through gravitational interaction or Roche lobe overflow. And then subsequently, we found 20% or more, minimum of 20% of planetary nebulae had a close binary companion. So there ought to be binaries then in this progenitor phase. So here's the observational sample of the 7 that I started with, and then I picked up that program again. But they're bright objects. 3 of them are oxygen rich, 4 of them are carbon rich. You can see some HST images that show the morphology. This is Sahai's classification. All of them have a bright central star. That's why, that one could get regular monitoring on medium-sized small telescopes to actually carry out this project. And then bipolar, elongated, multipolar ones. Okay, so I began this, we started this project in 2007, but to get more spectra and better coverage, I spoke with Hans, and we got time on Hermes, and Griet van de Steen was involved with this, and time on a telescope in Lithuania. So we could really get a lot of observations. And I've published some of this, and some of this is new in the last 5 or 6 years. But we have numbers that go from at least 100 to in the order of 400 radial velocities of these. And looking at these, the bottom line is we see the pulsations in them with very irregular amplitudes, but no indication of binarity. Nothing that looks like a significant period that would be attributed to a binary. So the results of this sample of 7 bright protoplanetary nebulae is we see pulsations or semi-regular. None of them have a longer period that could be attributed to binarity. At one point, I thought I saw in the data maybe a 1.8 year period, but the best data and more data doesn't support that. Maybe there's something longer periods, but I don't see that. So a generous upper limit for any binary would be semi-amplitude of 2 kilometers, well, closer to 1.5. So I can set some limits. Now you might say, but this is a bias sample. You pick the brightest ones. If they're bipolar and you see a star, maybe you're looking pole on to that. But models have been carried out from mid-infrared or CO imaging that show inclinations that are rather intermediate. So most of them appear to be intermediate inclinations. So I can get constraints on the period and the mass, assuming a primary of 0.6 and an undetectable amplitude of 2 kilometers. We can find that because I don't detect them, anything below this would be undetected. So at any intermediate inclinations, I should detect them if they're greater than about 2 or 3 tenths of a solar mass, unless they have really short periods. So setting some constraints on the binary population of this sample. So where are the binaries? These are protoplanetary nebulae. They're not spherical nebulae around them, but they're bipolar or multipolar. They're present but hidden in long periods, perhaps. Although they're too long, are they going to affect the shaping? they're hidden but low mass secondaries? Or are they present but within the atmosphere of this effigy? We've got stars there with sizes of 50, 60 solar radii. Are they hidden inside there? Are they in a common envelope phase? I'm no expert at this, but we've observed them for 35 years. We don't see changes in the spectral type, the temperature, the luminosity of these objects. That nothing to make me think that there's something going on in a dynamic scale within those. Is it merged with the post-AGB star? Well, there's no evidence to support it. They have if you look at the spectra, it looks like what you'd expect from an evolved single star. They're not rapid rotators. Did they have some form of grazing envelope evolution? Don't know what that, no evidence there, but, or are they single stars, or is there something else going on? Or is it planets that are affecting that? So it was disappointing. I mean, it'd be much more exciting to find binaries and to be able to more specifically determine the properties of these stars. But that's not the end of the story. So what are ways that one could move forward in determining and direct evidence for binarity in these, and seeing the stars essentially? One could observe a sample that's selected to be biased toward that. Ones with a high bipolar or multipolar morphologies that were very strongly shaped. Ones maybe at a high inclination, but you could still see the star to get spectra. Or we did try some that where you couldn't see the star because it was blocked out by the dense waste, but in the near infrared, there were some that we could see the object, but it was hard to get time to follow up in the near infrared monitoring. Or long period light curves, as we see in some things like RV Tauri stars. Ones with long secondary periods have turned out to be binaries. So that's another approach, and that's I've followed up on looking for light curves that not only have pulsation in them, but have a long secondary period. We could do targeted observations. So there's some that I've looked at with collaborators, others where we've used survey data. And of course, there's something in the Rubin Observatory would be very good for this, and some that are a combination of these. And so here are some results, and this one's published, but here's ASAS3 data. Now we know that those data are not very precise. Here is Assassin V data. In some cases, we have some data to help define those curves. Periods 5, 19, 10 years. Those are long. Here's another one, another sample. 5-year period, 7. And this is one with the RV Tauri star. So there's the pulsation in there along with the long secondary period of about 4 years. So 3 in the previous one and 3 here gives us a sample. And in fact, as has been mentioned already, one such object has been found, and that was, that's this one. So we found a 7-year period in the light curve and a 7-year period in the radial velocity curve. So this is by Manik et al. Here you see the radial velocity data, periods about 7 years, eccentricity 0.36. And here's the one real clear, solid binary in what I defined as protoplanetary nebula. Now, the others we want to continue working on, and then another potential candidate here is the Frosty Leo Nebula. These are the so here are the light curves where I found a period of 550 days, in addition a pulsation period of 51 days. This is the Assassin G data. When I independently look at the Assassin V data, I find a period of 540, 10 days difference. So I think that looks pretty good as a strong candidate for having a binary. I think Raghavendra may have shown image of it, but clearly bipolar nebula. We don't see the central star, so we're seeing some reflection off of the material around it. And then what's exciting, and this is very preliminary here, but this is the velocity curve, the differential velocity curve with a period of about 500 days. Very preliminary, but a good suggestion of another binary in a protoplanetary nebula. So that would be the second one. And let me just sort of wrap this up. Okay. Monitoring of these, we've started looking at these 7 objects with long periods, getting some preliminary velocities. There was a program initiated a few years ago, which we're starting up again, and this is done in conjunction with David Jones and Todd Hilwig and some others. And hopefully we'll have some preliminary results in a few years. Did I get a time sign?
Yeah.
Oh, I'm sorry. Gee, okay, sorry. Here, let me finish by putting up some final implications then. Excuse me. No direct evidence. Maybe there's planets or something around it. Clearly, these are not the precursors of short period common envelope binaries. And evidence suggests 2 ways to form a planetary nebula. One through the standard textbook way, which we've been looking at, and one through common envelope. Thank you for your attention.
The rotation rate is interesting, so I don't think you can say that they're not mergers, but I do applaud the sentiment that you would like to see a rotation.
Yes.
However, these stars are very large, there could be tens of our sun, right? So you might not see, eventually they have angular momentum in there, so once they shrink to white dwarf, they'll rotate rapidly. But potentially you won't see it while they are 2030. And so the question is, what limits can you impose on the rotation rate based on, say, the spectrum?
Okay, and I don't have an answer to that at the moment, but I mean, I agree. What I'm saying is there's no clear evidence by rapid rotation, but I'm not saying it eliminates a merger. Yeah, but maybe we can get a number for that.
Sinai is about 10.
Pardon?
V Sinai.
V sin I is about 10.
Width of the lines are pretty small.
Okay, I'll calculate.
How small? 10 or 20 kilometers. V Sinai. 10 or 20 what? So it's not a rotation, it's the width of the line, so it's the turbulence, all the.
So you cannot
see the rotation.
Everything put in there, pulsation, convection, and all.
Make me the link, please, from the person.
Look, I think you're doing, we follow you for many meetings of APN, you're doing a marvelous job actually, and you're pushing us. But I think also is correct, we expect some merger to occur, okay? If we have a white dwarf merging with a core, this is interesting, will be a type 1a supernova. Tomorrow or Thursday, I will discuss type 1a supernovae belong to this community, and we didn't discuss them yet here, which is the problem beside one poster, which I mentioned in Slack. But which star will merge, or not merge, will be destroyed by the core? These are low mass main sequence stars that did not manage to eject the envelope, but they're still spiraling in, and we see the nebula, so they ejected lots of material. So imagine a 0.2 solar mass main sequence companion spiraling all the way to the core and tidally destroy it about 1 solar radius. And this is now you have a new envelope material of 0.2 solar mass. mixing with the envelope or whatever. But say the envelope that was left is very low. So this 0.2 solar mass is tidally destroyed at 1 solar radius. Now it is inflated by the core to whatever, 300 solar radii. By angular momentum conservation, the velocity will be 2 kilometers per second, which you cannot find. The convection is even faster. So I expect slow rotation. Even
Okay.
if you have wind, it will slow it even more. So if it was a rapid rotation, then the binary is still there. Okay, but this
Right,
slow
right.
rotation can be merger, which actually is compatible with not finely. So these are merger. I would look at maybe the composition of the nebula might be a little bit different from the composition of the star or late nebula or something like this, because I expect the present envelope of the star to contain lots of mass from the tidally destroyed companion.
Okay, and let me just a simple response is that the atmospheres of these look like exactly what we would expect from a star that had gone up the AGB. We see molecular carbon and S process abundances on it. So there's nothing in the abundances that would make us suspect that something like that happened. I'm not saying it's strong, but there's nothing to suspect. But I hear you.
Okay, let's thank Bruce again. And now we have Ivan Gallardo.
Hello everyone, I'm Iván Gallardo Cava from Madrid, from Observatorio Astronómico Nacional, and I'm going to talk about circumbinary post-AGB disks. I'm going to split this presentation into 4 more or less. The first one would be a brief introduction about these sources. The second one would be new results that are now under review. Next, I will talk about Meerkat observations in the red rectangle, and finally, I will finish with greenback observations and maser emission. So, what is a circumbinary post-AGB disk, or what are these objects? It is a post-AGB or a post-RGB, but in this talk, all of them are going to be post-AGBs, a main sequence star, an accretion disk, a mini accretion disk around the main sequence star, a jet launched by the main sequence star, a rotating disk, what is the most important thing for me in this presentation. It is composed of gas and dust. And all these sources has in common that all of them present this significant near-infrared excess. All of them present a narrow component in the CO lines. And some of them with interferometric observations present a PV diagram like this that shows butterflies, that butterfly shape that nicely shows the Keplerian rotation. All of them present a radial velocity curve like this. That means that these sources present orbital periods that are in between 100 and 3000 days. And this is very striking because, according to models, there should be 2 populations. The first one should be those with very short periods, and the other one should be those with larger periods. I'm talking about thousands of days. But these sources, this sample, fall exactly in between. Sorry. Oh. Oh. Okay, thank you. This is a non-scale Python model that finally shows the Keplerian rotation of these sources. I have tried to represent all the elements present in these kind of sources. Both stars with the accretion disk, their launch jet by the main sequence star that are present in present in some of these sources, and also the molecular outflow around the Keplerian disk. Those sources, from a molecular point of view, can be split into two: disk-dominated and outflow-dominated sources. This is a disk mass criteria, which means that these dominated sources present a disk mass percentage of about 85% of the total nebulae, while outflow-dominated sources present a disk mass of more or less the 30% of the total mass. This is a disk mass criteria. But if we do an analysis like this, in which we study the luminosity at 1 millimeter with the total nebular mass, including both the disk and the molecular outflow, we find two populations. Those with a higher ratio are those dominated by the disk, and those with a lower ratio are outflow-dominated sources. This is important because these dominated sources should present a higher reservoir of large dust grains. That implies that those sources would avoid the creation of larger envelopes, but will help in the creation of larger body in the rotating disk. While outflow-dominated sources would present disks that would avoid the creation of larger bodies in the rotating disk, but would help in the developing of larger and massive outflows. There are 85 sources of this class. 31 have been very well studied in CO lines, and most of them present detection. We have detected CO in them, but there is a significant fraction of them in which there is no CO. Well, we have not detected CO. If we can do some statistics with this, and we know that according to this, there should be an arithmetic mean of 2.3 to -2 solar masses. But taking into account that we have a significant amount of upper limits, we should do some statistics taking into account these upper limits, which means sensory data. If we do that, now we know that all these sources will present nebular masses in between 10 to -4 to 10 to -1, and that includes both the disk and the molecular outflow. Doing that, we also know that those sources would present a typical mass value of 2.4 to 10 to -3. I remind you that including both the disk and the molecular outflow, and of course, taking into account the detections and all the upper limits of this sample. Now we are going to change topic, and we are going to talk about the red rectangle and continuum observations. The red rectangle is the best studied object of our sample. We see here the typical Hubble feature. We see here the PP diagrams of ALMA observations that nicely show the Keplerian rotation, and we also show density and temperature maps of the rotating disk. This is a continuum image from ALMA observations. What we see here is two components. The first one should be the disk. That is composed of gas and dust. But we also see a very central compact component that will represent free emission. Why is that? If we pay attention to the spectral index plot that I show you here, we see that the dust will present a spectral index of 2. But the central component presents a spectral index of 0.8. What happened? For wavelengths exceeding a certain value, dust emission is dominated by the free emission. But which wavelength range can be used to observe large dust grains? The answer is shown here. This is our very new 3 GHz Meerkat observations that confirms that the flux at 100 millimeters is absolutely dominated by the free emission, which means it's the jet launched by the mean sequence star. But what happened with the dust? All these sources present large dust grains in the rotating disk. But if we want to observe or to study those large dust grains, we can only observe them in this domain. So we can only observe them in the at 20 millimeters or so at most. This is in the case of the red rectangle, but maybe we can extrapolate this conclusion to the whole sample. Now we are going to change again the topic, and we are going to talk about measure emission. In the case of a circumstellar envelope around an AGB star, and in the case of an O-rich star, we can find three measures that very nicely trace the envelope. The CO measure emission is located in the very innermost region of the envelope. The water measure emission is located at 10 to 100 astronomical units or so, more or less. And finally, the OH measure emission takes place in the outermost region of the envelope at 10,000 astronomical units or so. But this is in the case of AGBs. But what happened with post-AGBs? These 10 sources were studied in detail in 2022 in 1 millimeter, 2, 3, 7, and 14 millimeters. And we conclude in this work that all these sources are very poor in molecular content, and that some of them present CO measure emission, that some of them present water emission. And now, thanks to our very recent green bank observations, we know that 18 and Hercules, IRAS 18, AI Canis minoris, IRAS 20, and R Scuti present OH measure emission. And all of them have something in common. All of them are outflow dominated sources, these kind of sources. We have not detected OH measure emission in sources that present a disk and a very weak molecular outflow surrounding the disk. This is, I show you here, the two sources that present the three kinds of measure emission, R Scuti and AI Canis minoris. Both of them, of course, in this kind of source, an outflow dominated source. Just for comparison, I show you also the CO, the thermal SIO. The next three rows are CO measure emission. The next one is water emission. And finally, the OH measure emission. AI Canis minoris present the typical U-shape OH measure that is typical of an AGB, and that represents a copious mass loss. This shape is also present in all the sources where we have detected OH measure emission, except for this guy, R Scuti, where we have detected OH measure emission with a very narrow component that it is almost coincident with the systemic velocity of the source. So I don't know what does it represent. But I know that we know high resolution L-band observations to know what is happening here. And finally, this is the conclusions of this work. These kind of sources, from a molecular point of view, present masses that are in between 10 to -4 to 10 to -1, including both the disk and the molecular outflow. Including the sensory data, we know that these sources present a typical mass value of 2.4 to 10 to -3 solar masses. Thanks to our MeerKAT observations, we know that at least in the red rectangle, at 100 millimeters, the emission is absolutely dominated by the free emission. But what happened with the last grains, if we want to observe them or we want to analyze them, we can only do it until the millimeter region at most. And finally, thanks to our green bank observations, we know that some of these sources present OH measure emission, and all of them that present OH measure emission are outflow dominated sources. And that's all. Muchas gracias.
This one's very bad.
Thanks for the talk, Ivan. With respect to the free emission.
Yeah.
Does that link to the temperature of the accretion disk around the companion? Or
Sorry?
where, so the energy is coming from the accretion disk around the companion, I suppose? And does it limit the temperature of that accretion disk?
This emission
Yes.
is being related to the free emission that I suppose that it is due to the jet launched by the main sequence star. or maybe for a H2 region in the very center of the disk.
Yeah, but can you derive some temperature?
No, not for the moment. No,
No.
this is a very preliminary result.
Temperature.
This is a very preliminary result, and I don't have these numbers
Okay.
for the moment.
But the free emission itself is coming from the jet or is coming from the accretion disk? Or is that unconstrained?
I suppose that from the jet. Thank you.
Anybody else? Okay, I have a question.
So what are the, are you able to measure the mass only of the disk or to disentangle?
Here?
So what are the typical masses of the disk around this object?
It depends. So the typical mass value of those guys should be 2.4 to 10 to minus 3. But we know that there is a disk mass criteria that split this population into two: disk mass, disk dominated and outflow dominated. For those sources dominated by the disk, should be like 80% of the total mass of this amount. But for outflow dominated sources, should be like 30% of the total mass for the disk. This is more clear in this plot. This is the total mass. In the case of this dominated, should be like 85%. For instance, the red rectangle, IRAS 08544, IW Carina, AC Hercules, those sources present a disk mass of like 80% of the total mass. On the contrary, those guys present this that total mass, but we have to take into account that the outflow is like 65 to 80% of the total mass. And for the whole middle, we need interferometric mass.
The other question was, for this object, are you able to measure some kind of accretion rate or this kind of thing?
Sorry?
Are you able to measure accretion rates? I mean, these are accretion disks.
No, this is the rotating disk and the outflow, the molecular outflow around the disk. Both the post-AGV components.
They are not accretion disks.
No. This is the mass of this disk and the molecular outflow. This is not the mass of this. No. Oh, sorry, of this. No, it's the mass of the rotating disk and the molecular outflow.
Okay, thanks.
But just to continue, we did a work in 2023, and the mass of the non-molecular content is significantly lower than the masses that we derive for the molecular content. So the mass of the total component should be the disk and the molecular outflow.
Okay, so I'll ask my question now. So the OH Mesa plot that you showed for AI Majoris, does the structure in that line tell you anything about the shape of the outflow?
I suppose that this would be very large, mostly spherical, because we don't have interferometric maps of this source, but we do have of this source. And in the case of this source, it is mostly spherical with two cavities next to the disk. We would suppose that this source should be similar, and taking into account these two peaks, we are measuring the size of the nebula. That more or less is coincident with the extreme velocities of the CO.
Okay, thanks. So let's thank Ivan again. And now I think it's Albert.
Just checking my votes. The normal time because I'm 12 minutes in this game.
Yeah, I think you'll get the standard. Yeah.
Thank you. Thank you. What a nice conference, isn't it? It's almost over today. So, yeah, there are two ways to look at binary stars in the planetary nebulae. The one of them is the English expression: see one star, see them all. By law, planetary nebulae should be limited to one star. Yeah. The other way is Leo Tolstoy, who said, well, every single star is the same. Every multiple star is multiple in its own way. This research came out of an attempt to simplify a binary system. I failed completely. So here you see the NGC2346, and you see a very nice nebula. It's only partly seen. This, I think, is an image from Arturo, and there's a very nice bright star in there. Here is the same object seen by the Hubble. What happened to the star? I don't trust telescopes that make stars disappear. So we started looking at that, and then things got complicated. There are some people working with me, Ursula, Patricia Whitelock, Joel Kastner. I've not checked this talk with them. So feel free to disagree with me. Okay, so we have an interesting set of morphologies. But one group that I was particularly interested in are the ones like this object, the helix, where you can see lots and lots of these globules and the spikes. These are bipolar nebulae, of course. You see this one pole on, but that's what it is. There is a dust disk around the central star, and about half the total mass of the nebula is in those globules, molecular hydrogen. And then we saw NGC 3132 from DRST, exactly the same thing. Lots of globules, the spikes, the disk around the central star. We have the ring nebula. In spite of being a ring, it's nice bipolar, exactly the same thing. Half the mass of the molecular H2. So we thought, is there a pattern there? All of them also, well, these two, all of them is not true, see those rings or the arcs indicating a binary with a period of a few hundred years. So my feeling was, add those all together. And do you have a period of a few hundred years, you get these large shells, the dust disks, is it all part of a pattern? Well, some things don't quite fit. The butterfly nebula, as NASA thinks it should look like. This is NGC2346, and it's another object where we know there are lots of molecular globules with H2. It has a dust disk around the star, that was also known, and it has these white lobes, which I would call the butterfly. I call these groups the butterfly nebulae, but other people use the butterflies for their own things. But this is the only close binary in this group. Known clone, it's a period of 16 days, a bit unusual period. So it's what is going on? And we looked at it to see whether we could get rid of it. The central star, as you saw in the first slide, is quite a bright object. It's an 11th magnitude star. It is not the central star. That is an A star, just happens to be a companion. 7,000, 8,000 Kelvin. And it is a 16-day radial velocity binary. That's been known for a long time, but this is the most recent data from Brown et al. And David Jones, I think. But you can see the period very nicely. Assuming that the inclination of the system is the same as the inclination of the nebula, you can try to get the masses. The primary mass you can get out of the H-star diagram, 2.5 solar mass. That gives a secondary mass of 0.37 solar masses, assuming that that inclination holds. Ionizing star, we know from models that it should be about 130,000 Kelvin. 170 solar luminosities, as all of these objects, they are on the cooling track. And so they're already evolved nebula. But this star you only see in the far UV. Now, obviously, this companion has to be this ionizing star. It's a binary. What else do we know about this? If you look at the spectral energy distribution in the wavelength here versus the flux, you can see here the star very nicely. But if you go to the infrared, beyond the micron, you can see a large dust excess at the location of the star. And so there is a dust shell close to the star, which is then somewhat separate. At the longest wavelength, it's hard to separate the nebula from the star, but this is all the star. And so there is a dust shell, a dust disk, you would now say, around the star. 16-day binary, that is too close for the dust shell, so make this a circumbinary dust disk, as we normally do. Notice that some of the photometric points don't fit particularly well. That has been a problem here. And in fact, the Pan-STARRS data we even had to delete completely. The Pan-STARRS cannot cope with bright nebulae and trying to get a star inside. Gaia also was not particularly accurate for this object. There is some scatter beyond that as well. I'll come back to that. There are problems with this system. One of the problems is that the period of 16 days is somewhat unusual. Now, I don't know how well this plot shows up. This is David Jones, is the name, catalog of binaries. This is the periods versus number of stars, and here you can see all these close binaries. Yeah, here is our object. Doesn't fit quite well, but it's not the only one with such a long period. There's one here as well. if you make a plot on a log scale, you get a much better looking plot, and you get here a linear relation. And actually, yes, it is not impossible that you get an object over there. This is ours one, but the chances are not high. So it's a peculiar period. It either should be much shorter or much longer. The mass of the central star is a little bit low, 0.37 solar masses. Well, it has to come from a system that had an A star in it. So originally it must be much more massive. It must have lost an awful lot of its mass. In a 60-day period, look at mass transfer or a common envelope, but none of these systems, Ørsted tells me, can do that. It's very hard to make a binary system with that period, final period, evolve to a 0.37 solar mass helium by 12. So this suggests there is a problem. And the problem is we're looking at the wrong star. The 16-day binary has nothing to do with the Planetary Nebula. It is just a normal A star with a normal main sequence low mass companion. It is not the central star of the planetary. I couldn't see a way around this. So much simpler system is what I wanted. But then I remembered I have seen this object before. My first conference as a student, 1987, believe it or not, I was at a PN conference in Mexico City, second year PhD student, lots of talks. I didn't understand any of them. I was a PhD student, but one of the things that was discussed was this object. And the reason was that just a couple of years before, the star had disappeared. After 80 years of being just bright 11th magnitude normal A star, suddenly in 1982, boom, it went. Came back a little bit and then went again several times. And in 1985, it came back. And by 87, the whole conference was talking about what happened here. It was easy, of course. A moon blew up. That was the kind of things that people were discussing. After that was less published. There was two more of these events happened, but very short. And maybe another brief event over here. Now, this was unique. Since this year, it is no longer quite so unique because it has been seen in one other object, WESB1, Butcha et al. And then Batterji et al. Yes, have published a paper on a similar event recently in another planetary nebula. That object is, they propose a white binary. Notice the obscuration is of the companion. And that is true for this new object as well. So what do? Well, you try to say, what kind of dust is there? So let's see whether I can do just a simple model for the dust disk. But I assumed I used gray dust, so no wavelength dependence, ignore all dust features. Let's just assume this is a debris disk. Then fragmenting moon, the grains are quite large, they have no features, it's just gray. And assume that the dust is around the A star because that's where you see the effect of the obscuration. What I need to do then, you can see here this plot, and I need two disks to fit it. One is a warmish disk, 500 Kelvin. The other one is much closer in, much hotter, 1200 Kelvin. I can't do it with just one disk covering the whole set of radii. This one is, the inner disk is about half an AU from the A star. The other one is about 2 AU from the A star. And that works. And the masses, 10 to the minus 8, 10 to the minus 10 solar masses. So say the mass of a large asteroid. Yeah, or a small dwarf planet. So, okay, that is nice. That seems to work. But then you look at, well, what by the scatter in the flux? And so Patricia Whitelock showed us a lot of her data that was unpublished from the SAO. And we published it and we discovered, well, here is the K-band flux. It goes very nicely along and suddenly it starts to brighten. Stays bright, fades again and back to its original. H and K, J, H, K all show exactly the same pattern. And the brightening is about the same in J, in H, and in K, a bit less than a magnitude. That is after subtraction from the star, by the way. So that is something I had not seen before. Note the symmetry of this curve. It is not something dust forms and then decays. That would give you much more of an exponential decline. There is something else going on. I said, where have I ever seen a shape like this? And I thought, this morning, when I looked at the weather report of the university, because this is the temperature profile of a typical day in Manchester. And they say, oh, a heating event, it's illumination. So if this is physics, you can have an idea, but you do have to have a model and do the calculations. So I assumed, well, here is the 16-day binary. Here is this dust disk. I just put the central star and planetary in an orbit around it, elliptical, and then here it begins to heat the disk. can that do? You have to change orientations. Here I pick an orientation of the disk in this direction. You can also do it perpendicular. And then the heating, of course, increases as the star approaches the disk and as the star rises, depending on the inclination between the disk and the star. So you get the star rise over the disk. So you calculate how much extra heat got in, you can increase how much the temperature increases by, calculate the flux, and see whether you can fit what you see. And here is the fit, and you can see here, it actually fits remarkably well. It is a bright day in Manchester. This is assuming that the disk is perpendicular to the major axis of the orbit of the Planetary Nebula central star, and then you get a nice symmetric profile. If you do it perpendicular to that, so aligned with the disk, then you get a dip here because the star goes to the plane of the disk at closest approach, so minimum heat. I actually had to add a thickness to the disk to make it not go down all the way to 0. But overall, you can see this kind of plot works remarkably well. Periods more than about 100 years. Eccentricity quite high, 0.6 minimum, 0.8 minimum if you have the aligned disk. Minimum distance 10 AU or about 4 AU, depending which of these possibilities you pick. So assessment, yes, it works. Long period, which is what I liked. Elliptical orbit, it's the symmetry of the bump, it fits it all quite well. Of course, it don't have many points at the plateau, and that is a bit of a pity. And then you say, well, what happened? Here you can see where we are. Here is the closest approach, the hottest disk. This is the place where the obscuration events took place. It is in this model where the central star went through the plane of this disk. And you think, tidal distortions. It was pulled out of its alignment. And so, yeah, maybe that works. It is very notably that the obscuration event started shortly before the heating, and then declined. Here is another one, and then afterwards there's one more, and then it stopped again. So it was related to how close the central star of the planetary was to the disk in this model. But maybe other models. So food for thought. This makes it a triple system. I was one more than I like. But is that unexpected? No. This is an A star. This is one A star. The central star of the planetary must also have been an A star. And binaries among A stars are very, very high. Most of the A stars have companions. Dust disk is circumbinary, but it's around the wrong star. So how can that be? Well, a debris disk. It is just a disk that is related to what the A star did originally. Or maybe captured ACB wind. Who knows? Velocity data suggest the nebula torus is quite asymmetric. You see the profile here in oxygen and in CO. So the density is quite up. So an elliptical orbit, yes, might be able to explain that. The secret law of physics that no one tells you about it, when you found the result you want, stop. But I decided to look at an HST image with a missing star. And it turns out it was taken in March 1997, exactly during the depth of an obscuration event. So you look at the image and you see, oh, what is that? There's another star there. Completely invisible before, but it was now visible because the A star was so faint. But the invisible star was revealed. 0.4 arc seconds away, 500 AU. The colors, well, only 2 filters, and the wrong filters, I wouldn't have chosen those. And the magnitudes are not inconsistent with the central star of a planetary. But it could be a white dwarf that is much cooler and further on the cooling track as well. If that is the true central star of the planetary, then all of this is wrong. Because that is far too far away. All obscuration events, everything I'm talking about, has nothing to do with it being a planetary nebula. That seems unlikely. So I prefer that this star is just an accident. But there are now 4 stars in the system. Yeah. Okay, final point. While the eclipse was going on, the minimum was always about the same. That suggests that the minimum light was another light source. And before the eclipses started, about for 30 years, there was a slight fading of the star in blue only. Well, photographic, for still photographic plates in those days. I'm that old. That suggests that the extra light that you see is scattering. Scattering of the A star off the disk, and as the eclipse approached, that scattering reduced, maybe because the line of sight angle changed. So there is a scattered light contribution in this source as well. So conclusion, 346 is no longer the exception. The 16-day binary has gone, replaced by lots of other stars, but it is at least back in what I call the butterfly fold. Disks in planetary nebulae may be around the wrong star. They may include debris disks, so predating the planetary. And for higher mass stars, binary is so last year. Yeah, it might be multiplicity with n rather larger than 2, and that is not unusual. And finally, a common envelope bites the dust. Sorry, David.
I'm happy it's just still related to because we've already found 2 other systems where there's an A-type binary, it goes to the center of the N, and it's just a field star system that we've now. So as long as it's still related, it's fine.
Thanks, Albert. So it's not a post-common envelope planetary nebula.
No.
So then remember that yesterday I said that there were 3 systems that show CO and just 2 now. And it's a pity because this one was one of the outliers, which was the only one, which was massive. It was like 0.7, 0.8 solar masses or so. So no.
Yeah, that is why I want to get rid of it. It polluted our sample.
It's also was the most massive companion that we had as well. So all of the other post-common envelope companions are late K or early M. So we had this outlier with a long period and very massive, so it didn't fit anything. So you solved all the problems.
Good. Can I have my bottle of alcohol now?
So I just wanted to ask for the first observation event, obviously, I might have missed it, but with the fluctuations, what exactly the cause was for that, and why we don't see that in subsequent obscuration events?
That is a good question, actually. The obscuration, of course, is dust. It has to be. And it was dust that suddenly came in front of the star. It is not clumps, not orbiting clumps, because they lasted far too long. The tangential velocity, well, Roberto Mendez did a lot of that work, would have been only about 1 kilometer per second. That is not fitting the orbital velocities. So it is possibly more like a disk. And then the edge of the disk gets in front of the star, and then the star is suddenly gone. And so a disk seen edge on can be highly opaque. And I would expect, it wasn't how it was interpreted at that 87 conference, as far as I remember, but that is what we now know happens. And in cases, I mean, L2 Puppis, an HCP star, is cut in 2 by a dust disk. And so the dust disk seen under the light angle is very opaque. And it was something like that. But then you have to explain why it didn't happen for 8 years, for 3 years, and then a couple of events after that. And that I would think is tidal distortions in that disk, where it may be pulled out of its plane.
Yeah, it was just more. Sorry, it was just more about also why we then got to that the subsequent ones. Obviously, okay, fair enough for the first one, but then it's kind of a lot more simplistic.
Yeah, well, I've tried to visualize how the forces on a disk that is tilted with respect to its binary system at the center and with a third orbit around it, how that works, what is stable, what is not stable. Nothing is stable, I think. So you get all kinds of interesting movements of that disk, in my opinion. But the math of that is beyond me.
Okay, I think we have that for one last.
Could you have some highly complicated situation near the short period system where you have like some disks that are edge on and block the star and other disks aren't and get heated, and you just have this big mess when the star kind of comes near its 2 friends?
Well, you can try that. Of course, having up perpendicular disks is going to give you collisions if they're too close. And as far as you can see, the disk is only around that A star and its main star companion. Well, if there is a disk around the center star of the planetary, I'm not sure I would see that. And those are just far enough apart that wouldn't interact. So what I see is that debris disk, I assume it's a debris disk, being pulled out of its line of its plane into the line of sight from us. I would think it's the hot disk that is being affected rather than the cold disk, but that is just based on distance to that star. But yes, you can make the system very complicated, but it gets too complicated for me to keep in my mind.
Okay, so let's thank Albert again. So I think now we go into the discussion. Jason, do you want to join me? So we can really do observations versus theory. So I have to give the.
Yes, one comment. Remember, we are on YouTube, so it's important to use the microphone. And it could be better, I know that we are not going to do that, but if you name yourself before starting speaking, so that people know on YouTube who is talking.
Okay, so before we go into discussion, I'm going to give over the alcohol. Because I think we get some really nice questions from young people. So, Tom, you already owe me a drink, so I can't consider you. So then obviously, predictably, it will go collectively to the group of Jan Kam. Please, John. Okay, so does anybody have anything that they want to add to the discussion?
Rogelio for asking. So I have a lot of questions right now because this is really new to me, but if I understand correctly, well, when these systems undergo a common envelope and they enter like a proto-planetary stability phase, they do not necessarily form a planetary nebula, right? So in one of the presentations, they mentioned that maybe it is a single star that is evolving, and this is going to form a planetary nebula. Then, I was thinking that what about planets orbiting the central star? Will the planets be able to distortion like the ejections during the AGB phase enough to cause the multipolar morphologies we are observing in planetary nebulae?
I can maybe say something. I mean, I would say that, you know, the planets are all going to plunge into the star. They will all be highly disrupted around the core. And then again, you're tapping into that extra factor of 10 energy. And so they should be able to at least inject the envelope. Whether, you know, that disk is going to tilt and launch multiple things in different directions, I don't know. But it would at least be able to, for some fraction of planetary systems involved, it would probably blow off the envelope and there'd be no planet left.
Remember as well, from a morphological standpoint as well, not all planetaries are super bipolar.
Right.
Right. So a huge fraction, like 50%, are just not spherical, not bipolar, some elongated. Right. So a planet will definitely be able to make an elliptical nebula or something vaguely axisymmetric, but maybe not something as elongated as 2346. So
Just very additional comment to that. You need a kind of a fat planet at the right distance to go in at the right time. And there aren't that many of those. You need kind of super Jupiter level. So then the question is how many you got, even if they do all the things you said.
anybody else?
I mean, not necessarily has to be at the exact position, but the dynamical evolution of the planetary system can keep some of the massive planets closer to the star, but they don't have to be already in the
Scattered.
Yeah, I would like to add also, Raúl Maldonado here, that, for example, now that we saw the debris disk around the A star, maybe we have seen a destruction of planets that produce the debris disk, because I suppose that before the planetary nebula was formed, the planetary system was stable, and when it evolved, then some planets became destabilized, and that maybe produced this chunk of dust, the debris, and then after that, now it's more relaxed, I think.
But yes, it is certainly true that the planetary system will be destabilized as the star loses mass on the AGB, and all kind of resonance may kick in, and things are thrown around. You get the late head bombardment all over again. And I think that was what people had in mind when they talked about exploding moons. It was really asteroids hitting each other and debris disks forming. But remember, this is not the central star of the planetary. And the AGB star was the other star. The debris disk that we see is seen out the A star, And what I think is the central star of the planetary is too far away to really have affected that. And so there's no reason why the A star should have been affected by that. But yes, and certainly for planetary nebulae, central stars themselves, you would expect that this effect to play a role.
And I will answer you. The answer is yes. Yeah, I wrote tens of papers on planets, you can search for them. But, and it's, people talk about that you need, it cannot be a too massive star that the planet will not influence it. But the planet includes also brown dwarfs, but there is a desert brown dwarf. So, but planet can influence. And the big question is how large a star would be on the HGB relative to the RGB. Okay, so canonical evolution gives them not much, and people mention it. But most of the mass laws that we derive from observation are of stars that I think are binaries. We define what we call a J-isolated star. J-isolated star is J-isolated star, J's angular momentum. So imagine the sun. The sun will be an isolated, J-isolated star, has planet, but angular momentum will not increase very much. Think the mass loss rate will be lower. And if you run stellar evolution, MESA, or any code you have, with a little bit lower mass loss rate on the RGB and AGB, it keeps more mass to the end and it expands quite a lot on the AGB and can swallow far away planet on the AGB. In that case, the planet has enough angular momentum to spin it a little bit and it will be destroyed on the core. And Jason also did work on that, and also and I worked on planet. But so the answer is yes, some elliptical, not bipolar, planetary nebulae might be shaped by planets. So, but there's lots of literature on that. We don't need to discover again. We should go and expand this literature, because I think really some planets, especially 5, 6 solar mass, Jupiter mass will do a lot. So look for my papers, I don't know, for the last 35 years.
Thank you. A slight word of caution when you talk about planets. I mean, you have to get Earth out of your mind. Okay, I mean, these things are sort of super Jupiter. Super Jupiters are gas balls. And there's two things. One is that these gas balls can evaporate, right? These central stars are jolly bright and hot and all that good stuff. So a planet would in fact possibly be a source of a disk, as it were. The second thing, if you want to worry about the influence that a planet, a super Jupiter planet has on its surroundings, the geometrical size of that planet is probably dominated by its magnetosphere and not by its physical size or by its mass. So it's perfectly possible that a super Jupiter with an accompanying magnetosphere comparable to Jupiter but then scaled up would have a very strong influence on its surroundings. This surroundings could be a disk or it could be a star nearby.
So yeah, these are the real planetary network. No longer known. Anybody else? Otherwise, I think we're more or less at time now.
So first of all, we forgot the jet lag. Remember Bruce, the Carthagians had just found that the oldest PPN had the jet lag in the bulk of the nebula by about 100 years, was it? And so this must be a clue. The second thing is whatever you do with those binaries, they better make you a jet with a high momentum. And you can't do that with wide binaries, just can't.
Don't do it with what?
Wide binaries, it's
Not
just.
even if they're eccentric.
Hmm?
Not even if they are eccentric.
But that doesn't. Well, let's talk tomorrow. And then finally, I just did the calculation with the good help of ChatGPT. So you may not trust it. So it's very, very hard to get away from a relatively high rotation rates for post-AGB stars. I use the 30 solar radii, 1 solar mass post-AGB star that engulfed the 0.05 solar mass companion coming from the surface of the AGB. And you can fiddle all you like with the numbers, but you get about 40 to 50 kilometers per second rotation right now. I don't even know if that's breakup speed or not, but Of course, a bit,
It slows down more than it speeds up when it contracts.
and there might be some fluidity.
No, it loses mass before it contracts, so it slows down.
Okay, but I think that this, I'll take a better look, but the question is whether we already have a datum that these post-AGB stars are going at, you said D-Sinai 10? months?
Yes.
Yeah, so this is quite slow. Anyway, a point perhaps something to work.
So, any announcements, Martin?